In this video, we're going to connect what we know about exponential functions and really relate it to the graphs of exponential functions. Before we begin, there are a couple things to remember. Again, we have two different kinds of exponential functions. We have exponential growth and we have exponential decay. Growth, for our situation, is when our a value, or our starting value, is going to be greater than 0, and when our common ratio is also going to be bigger than 1. So that's when our graph starts low and gets high very fast in that curve shape. Again, please recognize that we never go underneath the x-axis. Our second case is exponential decay, which is the opposite. We're going to start big and get small. But again, we're never going beneath the x-axis, and that's because our starting value is going to be greater than 0. But since this is a decay, our common ratio, or our b value, is going to be between 0 and 1. So now let's apply this to a couple different types of questions. The first question, using the picture to the right, which of the graphs is the graph of f of x equals 2 to the x? Explain your reasoning. Well, when I look at this picture, I see 4 different graphs. I have graph A, which is the blue graph, graph B, which is red, C, which is purple, and D, which is green. To figure out which goes with which, I need to look at this equation and determine what kind of graph am I looking for. Well, in this equation, I automatically see that my x is the exponent. So I know that this equation is exponential. So I'm trying to find the exponential graph. Well, when I look at graph A, this graph starts tall, gets smaller, and then curves back up. Well, I know that can't be an exponential function, because exponential functions either grow or decay. They're not going to go down and come back up on the same graph. When I look at graph B, this one starts low, has a curve to it, and from what I can see, it keeps going up forever. So graph B could be an option. Graph C starts low. It looks like it's going in a straight line to me. Remember, straight lines cannot be exponential because straight lines are linear. Graph D, same thing. Straight line, it's linear, can't be exponential. So I've narrowed it down to graph B being my only option. But my question says to explain my reasoning. So I think it's graph B because both the graph and the equation are exponential. Let's apply the idea of graphs to another question. The graph above shows a comparison between population growth and technology use for a 90-year span. Part A. Which graph, population growth or technology use, show exponential growth? Well, by looking at the graph, I see a linear function and I see an exponential curve. So I want to know which one is the exponential curve? Well, that's technology use. Part B. Summarize the characteristics that differentiate a linear and an exponential situation. This word differentiate really just means what are the characteristics that are the different pieces between being linear versus being exponential. Well, I know that linear makes a straight line, and exponential makes a curved line. So one of the characteristics that differentiate between the two is a straight line versus a curved line. Another thing that I know is that something that differentiates the two is that linear has a pattern of adding, while exponential has a pattern of multiplying. let's look at part C. Write a statement for each year below, comparing the population and technology use. Year 40. So I need to look at my graph and find year 40. Well, at the bottom it says time in years, so I know that I'm looking at the bottom line at year 40. Well, that's right here. So a statement I could say about year 40 is that population growth was much higher than technology use. Now it's asking me to look at year 80. Well, at year 80, if I want to compare the two, it looks like they crossed. So population growth equals technology. And then in year 90, which would be right here, my graph kind of ends, but I can picture both of these lines going on, and it's pretty easy to see that population growth would now be much smaller than my technology use. And that would make a lot of sense because we know that one of the big things about exponential functions is that exponential functions will always grow faster than linear functions. So since my linear function was population growth, eventually it's going to have to be smaller than my technology use.